Okay, let us start with a brief discussion concerning the nature of electric fields and where they come from, and then I'll give you a hint how to do the homework problem that involves calculating the electric field from 2-point charges. Okay, so let's look at this problem. Okay, first of all, you really need to understand, just fundamentally, where does an electric field come from? Well, electric fields come from the fact that charges exist, and they exist as like isolated monopoles. What that means is we can actually have a situation where we have a positive or a negative amount of charge that's isolated in space. So basically, electric fields owe their existence to charge. So we could also say charge is the origin of electric fields. Now, Michael Faraday came up with this convention here of using these lines to represent the electric field. So let's look at a positive, and I'm going to call it a source charge because it's a source of an electric field. Okay, conventionally it was just chosen to be this way. We could have done it the other way, but how we've chosen to depict electric fields is this is the convention. If we have a positive charge, which I'm using green because that says, see how that says go field? The positive charge acts like a discontinuity in space. In other words, the electric field just comes from nowhere, from a point in space, and emanates outward in all directions. Okay, so this is called a divergent electric field. The field is a vector field, and it has the property of vergence. It converges or diverges, in the case of positive charge as the source of a diverging electric field. So similarly, a negative charge, which we'll use red for stop field. See, green light, red light, right? Stop field is a converging electric field. The electric field lines run into a point in space and just disappear. So it's like these are like discontinuities in the fabric of space-time. I mean, isn't that a weird way to think of what is charge? We really don't know, but some modern thoughts suggest that maybe it's just like a defect in the structure of space-time itself, so that other charges will either be attracted or repelled to those points in space. I mean, it's kind of strange, right? But anyway, so another way to look at the direction of the field is to consider what happens if we use a positive test charge. So these are the source charges of the electric field. If we put a positive test charge in this space, it will move in the direction that the electric field points. And that makes perfect sense. Why? Well, if we put a positive test charge out here, won't it be repelled from this charge and attracted to that one? And how you would determine exactly how it moves is given by this picture here. This is when you connect the lines, and that's called a dipole field. Two charges of equal strength. The electric field lines actually, they're continuous in this region, but they're actually discontinuous because they emerge from this point and they converge to this point, right? So they diverge from here and converge to here. And if you put a positive green charge, let's say right here, a positive test charge, it would actually move along this line and go right to the right next to the red charge. It would move in this direction. So that's the direction a test charge would move. So this gives the direction of the electric field at a point in space. So what you notice from this is that if you try to calculate the electric field from an assemblage of charges, then the only really simple case is something right along this line, because it's either going to point right or left. Anything else requires vector addition, and that can get tough, right? Because you have to decompose the vectors into their x and y components. Okay, so let's consider the homework problem. Now, here is a problem that's very similar to your homework. I've changed the value of the charge, and I've changed the distances, and I've also changed the point from where we're calculating it. Okay, so in your homework problem, you've got a couple of charges over here, and you've got to calculate the electric field here, right? It's like you remove whatever charge I put at the origin, just take it out of the problem, and then you're going to calculate the electric field from two other point charges. Okay, so let's look at this case. In this case, we want to consider our point charges here and here and calculate the electric field here at this big X. Okay, now, here's what I've done. I've labeled, it's nice notation. I've labeled Q1 to be plus 6.0 nanocoulomb. Now, a nanocoulomb is 10 to the minus 9 coulombs. In your homework problem, I'm using microcoulomb. That's 10 to the minus 6 coulombs, right? Okay, so these are going to be weaker electric fields because there's not as much charge. Now, Q2, which is right here, this red charge, right? Q2 is going to be -2 nanocoulomb, okay? Now, we also should label in a logical fashion Q1's position from the point in space, where we need to calculate the electric field, which is right here. So D1 is at a distance of 1.2 meters. So a straight line to there is 1.20 meter. And Q2 is located a distance 0.55 meter, right? Now, here's how you do it. Now, here's what makes life really easy. I highly recommend that you never, ever, ever, for electric force and for electric field, just those two cases, electric force and electric field, they're both vectors. Do not put the sign of the charge in your formula. Don't do it. What you want to do is use common sense to dictate what the direction is. And we'll see that as we work through this. It's very simple. Okay, so first of all, we need to use superposition. Every single charge contributes to the electric field. Well, in this case, there's only two. So we're going to sum E1, which is the electric field due to Q1, and E2, the electric field due to Q2. Okay, now what's our formula? Notice that basically we have the electric field is defined right here. Electric field is defined as electric force per unit charge. Now, remember electric force was KQ1 Q2 over R squared, right? Or over D squared, R squared, whatever you want to call the distance. So, but electric field, notice that we're dividing by a charge, and that charge that we're dividing by would be the test charge. So, see, these are your source charges. They're the source that's what this Q is. When you're talking about electric force, you have two charges that interact together, right? So in this case, we only have one source charge that contributes to the production of an E field. Okay, so you take K, the coupling constant, which is 8.99 times 10 to the ninth, and then you multiply it by the ratio of the charge to its distance squared. Remember the inverse square. So basically Q1, which is that, over D1 squared. Now, what direction is the field pointing? Well, obviously electric field lines point away from a green charge, from a positive charge. So they're pointing to the right. So it's still pointing to the right over here. The electric field from this charge would be pointing that way. Now, another way to look at it? What would happen if we put a positive test charge right here? Wouldn't it, if we ignore this one completely and put a positive charge here, it would feel repulsion. So its direction of repulsion would be a straight line right like that, right? So we know the direction is plus x hat. That's the x direction to the right. Now, what about the E field from Q2? Well, like I said, don't put the sign in there. It's a negative charge. But what you do is you have K times the magnitude of the charge, which is 2 nanocoulomb, over D2 squared. And D2 is, of course, it's going to be closer. Now we know that field, if we put a positive test charge here, it would be attracted to this charge, right? So the electric field's pointing this way to the left. So that's why I put negative x hat. That's the left direction. Okay, so if you want to do this, what I call brute force, it's very simple. Just plug in the numbers, and you know it's positive because we've defined the positive x direction, right? See that? See the numbers? Now you can run this through a calculator. And then this minus, we see this is a minus, so we're going to subtract off the contribution from this charges field. So that would be here's your parameters, the K constant times the charge over the distance squared. So what are the key aspects? Do not put the sign in your charge. Try to figure out what direction it's pointing from common sense. 2, don't forget about your coupling constant K. 3, another important, don't forget to square your distance. Don't forget to use MKS units. Coulombs, like a nanocoulomb is 10 to the minus 9. A picocoulomb is 10 to the minus 12. A microcoulomb is 10 to the minus 6. Be careful when you read the problem. And also distances. Convert centimeters or millimeters or micrometers, whatever, to meters. Now, there's another fancy way to do it. This is just brute force. We could obviously see how K is a constant factor. You could factor out K and then factor out this minus sign and just write it. See how I wrote it like this? You might like that. For those of you that like to do a little bit more sexy looking math there, it looks better. You can kind of see what's going on here. It's You can just look at that and see it, and look at the picture and look at that. Okay, anyway, I think that'll give you a nice hint for the homework that's due tomorrow. Sorry this got out so late. I've had some issues with my laptop. What a disaster. Anyway, I'll talk about, in the next videos, I'll talk about electric potential and electric potential energy, which is easier. And we'll talk about that in a minute. All right, bye.